Hi everyone, my name is Marius. I'm an engineer at Arcium. I'm here today with Nico, our CTO and co-founder, and in this video we're going to talk about the Arcium network. So please, Nico, could you explain to our audience what the Arcium network is?
Yeah, for sure. So the Arcium network consists of four main parts, and these are the first one, MXEs. The second one is the clusters. Let's write that down over here. The third one is the nodes. And the last one is the mem pools.
All right, let's start with this first mysterious term, the MXE.
Yeah, so MXE stands for MPC Execution Environment. So let's write that down as well. MPC standing for multi-party computation. Execution environment. And they basically define everything that's needed to run an MPC computation on the Arcium network. So that basically includes three main parts, which are first here, computation definition, which defines what is actually meant to be computed. More on this in a second. Data objects, which define, what data are we actually working with here. And last but not least, which is already written down conveniently, the clusters, which they themselves then actually define who is actually doing these computations.
All right, thank you. Well, MXE for me at least sounds still pretty abstract. Could you please explain us where such an MXE actually lives?
Yeah, for sure. So the place an MXE lives, and the place more broadly Arcium as a network actually lives, is you can think of it really like, a network for executing MPC computations that can be bound to pretty much anything, whether that be as a coprocessor to a blockchain. So, let's say we have some blockchain such as Solana over here. Then you can think of it, it's processing its blocks, doing its transactions. And then we have our Arcium network, living over here, consisting of a whole bunch of different nodes. And then it can communicate together with the blockchain. So the blockchain can tell it, hey, compute this MPC computation for me. And the Arcium networks does it, responds. But of course, it's not only limited to blockchains. It can also, do this with, some server, for example, where it computes MPC computations for it. And MXEs themselves then are basically the interface that we use to communicate between some outside thing, be that a blockchain, be that a server, be that whatever, and the Arcium nodes. So, in this case, an MXE would be living right, that's small, right here.
Okay, I think we got it. Thank you very much. Yeah. You mentioned three key points that constitute an MXE, sorry. Could you first start with explaining what data objects are?
Absolutely. So, data objects, I think as the name is a little bit self-explanatory too, are basically what, if we have an MPC computation that's supposed to be ran, define where the data for the MPC is actually supposed to be sourced from. And you can think of them in regular programming. You might know what a pointer is. And, basically they're a reference to where MPC nodes are supposed to fetch data for a certain computation. So, you can think of them, we have some data object right here. And that could point to, an account, for example, living on a blockchain that stores some data. So you could point to, some piece of a blockchain where there's data stored that there's supposed to be computations done with. Or, of course, it could also point to some off-chain source. It could point to, some database, for example. Oh, okay, let's write DB next to here. So basically it points to where the data is supposed to be fetched from. And in addition to that, it also stores a hash and a zero-knowledge proof so that nodes can actually verify that when they fetch data from the blockchain or fetch data from wherever, that this data actually matches what the person who created the data object in the first place actually meant to reference, so that there isn't some problems with fetching the data from the wrong place by accident.
All right, thank you. So we covered the data objects. Sorry. There's as a next point, let's look into a computation definition.
Yeah, for sure. So, if you can think of an MPC execution environment, a little bit like a program that has has memory or has data on which it computes stuff. Of course, the other important part that a program has is it also has the actual functions, the actual function calls that it executes. So computation definitions are a little bit like functions in a programming language. And if you think about how functions in a programming language are structured, they usually look a little bit like this. So you have some accessor, then you have some name, it's called my function. Then you have some input parameters, so I don't know, you have uint or something, and then it returns, it specifies some return value. And finally, the most important part probably, let's write that in here, is the body of the function where you actually say what's supposed to happen. So this is a function in normal programming language, and a computation definition is very similar to that. So just like a normal function, a computation definition has an accessor. So how you have public, protected, private, whatever for normal functions. Computation definitions, it's similar. You have an accessor where you say, is anyone allowed to execute this computation definition, or is just smart contracts allowed to do this, or is only this specific actor allowed to do this, stuff like that. Then the second part is you have the parameters. So, same idea. In a computation definition, if you have a MPC computation, you probably want to tell it, hey, this is the data I actually want to do the MPC computation with. So this could be, data object or raw data that's passed in directly, what have you. Next part is, the return type. So if computation definition, same thing. You run an MPC computation, you compute some kind of result. And then the question is, what do I do with this result? Do I post it on chain, or do I throw it away, or do I do I don't know what with it? And last, but definitely not least, most importantly, we have the function body, which basically specifies what is actually meant to be computed. And that's the same thing for computation definition. It has a circuit, which is just an MPC program, basically, which defines what are we computing, what are the different steps to go from our parameters to our result. And yeah, they're basically like functions. So that means if you have an MXE, it can have multiple computation definitions.
All right. Thank you very much. So we have covered the data objects. We have covered the computation definition. The last missing piece are the clusters. So what does actually a cluster consist of?
Yeah, great question. So, let's say we had an MPC execution environment without clusters, then it wouldn't be very useful, right? Because then we'd say, okay, we have a function that we want to run, and we have data that we want to run, and that would basically be like if we had a computer that has a program on it, that has memory on it, but that doesn't have a CPU. So, it wouldn't be very useful. So clusters are kind of like this. They're the ones that actually compute the, what's specified inside of computation definitions. And as you can tell by the name of MXEs, MPC, multi-party computation, you can't really run multi-party computations if you don't have, as the name says, multiple parties. So for that reason, every time that we have an MXE, let me make a little space here. Every time that we have an MXE, right here, we associate, to get to it, a set of nodes that essentially all know each other and work together, which is what we call a cluster. So basically, anytime the MXE says, hey, I have this computation definition and this data and these parameters, I want to compute some kind of MPC. These clusters are the ones that then actually fetch all that data, then compute, whatever the user requests based on the MXE to be computed.
Okay, thank you very much. So you said a cluster consists of nodes. Who can actually run such a node?
Yeah, that's a great question, because Arcium at the end of the day is really just a permissionless protocol that allows you to schedule and execute MPC computations from a blockchain, from a server, from anything. So that means, the same goes for nodes and the same goes for MXEs. Anyone can create and anyone can operate these. So it means for a node, you just need, a computer essentially to run the node software on, and then you just deploy it, and there you go. There you have a node. If you want a cluster, same idea. You need to, find a couple other nodes and say, hey, let's make a cluster together. Then you have your cluster. MXE is basically the other end of it. You just have to download our dev tooling, and then you can write up your own your own MXE doing whatever encrypted computation you might be interested in. And you can deploy it directly, on chain, for example, as well. The only part that requires perhaps a little bit of coordination is, here the arrow, linking the MXE to a cluster that actually computes stuff on it. And the reason for this is that clusters can choose which MXEs they accept. So if you're operating a cluster, you might say, oh, I don't want every MXE that exists to be able to use my cluster for computations. Instead, I only want, this one specific MXE over here, or only MXEs deployed by me, or anything like that. But of course, you can also say, oh, I'm making a cluster and anyone's allowed to link an MXE to me. So yeah, overall, it's 100% permissionless in that sense.
Okay, awesome. Thank you very much. There is one last piece to make up an MXE, which is the mempool, which I assume is a very crucial piece. Could you please explain to our audience what the mempool is?
Yeah, you're correct. The mempool is a very crucial piece. So let me illustrate this by creating a second MXE here. Let's say we have MXE number 2, and over here we have MXE number 1. And our MXE number 2, of course, also has a cluster associated to it. So, let's say that's like these guys, and it also has one from this one. Then let's draw a circle here so it's a little bit easier to see. And that's the one that our MXE number 2 is associated with. Now, for the sake of example, as some of you might know, mempools are basically just a place where computations, or in the case of blockchains, transactions live and get stored before they get executed. Now, let's say we had a global mempool. So that means we had one mempool, and MXE and MXE1 and MXE2 share this one, and every other MXE that's running on the Arcium network also shares this mempool. Then we might run into some issues, because let's say MXE number 1 is super popular. Everyone's sending transactions to MXE number 1. However, MXE number 2, is not that broadly popular. It has a few people using it, but overall it gets far less transactions or computations. What would then happen is we'd have inside of our mempool the computations for MXE1 clogging everything up. So that means these nodes here that are in the MXE1 cluster would constantly be busy, and they'd be very happy because they'd be making a lot of fees. And the users of MXE1, they might say, oh, I wish my transactions or my computations were going through a little bit faster. But it is what it is because it's so popular. However, the people related to MXE number 2 would not be very happy, because they'd say, hey, how come it takes so long for my computation to actually be processed when in reality, the nodes that are working on MXE number 2, they don't have any work to do. And same for the nodes that are part of MXE number 2. They would also complain. They would say, hey, this is so unfair. Like there is computations to execute for MXE2, but we can't use them because the whole mempool is clogged up by stuff from MXE number 1. And so, I think the way I phrased this makes the solution decently apparent. The idea is then we create 2 separate mempools, or one mempool for each MXE. So let's write this down as well. So we have then mempool 2 for MXE number 2. Whoops. And we have mempool 1 for MXE number 1. And this essentially solves a problem then, right? Because that means the people who are interested in MXE2 put their computations in mempool 2, which isn't very full. And so that means the nodes in cluster number 2, they can look in mempool number 2, fetch their computations, and don't even have to worry about what's going on in MXE number 1. But one thing that's interesting here is that you might notice what happens to this guy here, right? Because he's part of mempool number 1, MXE number 1, and MXE number 2. So wouldn't this kind of screw him over, because he's already so busy with MXE number 1. Now he also has to deal with MXE number 2. Like, what happens there? The advantage of this is that MPC, unlike other types of computations, is communication bound. So what that means is that most of the overhead doesn't actually come from computing things locally on your machine, but instead comes from communicating with other nodes. And the good thing about that is that when you're communicating with other nodes, even though it takes long, it really doesn't require much work or much strain on your machine at all. Because all you're doing is you're sending someone to something else, and then you basically just sit there and you wait until you get a result back at some point. So that means in reality, if you're bound by that, you can run a lot of MPCs in parallel, because most of the time in most of your MPCs, you won't be doing anything except for just waiting. So for that reason, we optimize our system to take advantage of this ability of MPC to be very easily parallelized by implementing multiple mempools.
All right, thank you very much. So it's a pretty cool design of having multiple mempools. You were mentioning computation several times. Could you please explain to our audience what a computation flow actually looks like?
Yeah, for sure. So I think that's a nice way to bound everything together. Yeah, I don't think I need to erase anything. So let's say, we have MXC1 here, which is, very popular, and could also not be very popular. That's not really important for this example. But let's say we have, our little user here, Bob, and he wants to, do a computation on MXE number 1. So the first thing he has to do is he has to queue his computation into the mempool. So that's step 1. Then, once it's inside the mempool, the nodes will continuously check the mempool, and as soon as they have free resources, they'll check, okay, is there another computation that we can start? If yes, if no. Let's say they have some free resources, so they look inside the mempool, and they see, oh, Bob's computation is here, and it's waiting to be executed. Cool. So that means they'll look inside of here, see that there's something there. And then basically the next step is they say, okay, since we know that Bob's computation is in the mempool, we're going to need, the data objects that Bob wants to compute on. We're going to need the computation definition of what Bob wants to compute, and any other, metadata that might be stored inside the MXE. And yeah, that means they fetch all that stuff. And then once they basically have fetched all the information and all the data that they might need to compute Bob's computation, the next step, I think, pretty apparent, actually, computes the MPC that Bob requested. So they do that, I think that's, 4. They compute the MPC that Bob requested, and then, they compute it, and then at some point they say, okay, we're done, we have Bob's result. And then at that point, it's just a matter of posting it back to wherever Bob requested it from. So, if Bob requested it on chain, okay, we post it back on chain, step 5. Or if Bob posted it via some other means, we post it back to wherever. And yeah, I think what might not be super apparent here, so I just want to have said it, is 1 points here to the mempool. But of course, the mempool along with the MXE, of course, they live on chain too. So, at the beginning, Bob submits on chain, and at the end, Bob also gets a result on chain. For example, Solana.
All right.
That's the flow.
Thank you very much for this explanation. You were mentioning that the result is getting posted back. How can you make sure the result is correct? For instance, if one of the nodes decides to deviate from the protocol, or even decides not to execute the protocol at all?
Yeah, that's a great question, because our blockchain might be relying on thousands of nodes or hundreds of nodes, and so for that reason they have what's called dishonest majority assumption. So they assume that at least, for example, 51% of the nodes are honest, and if that's the case, then everything runs correctly. And that works because if you have thousands of nodes, corrupting half of them is going to be a ton of work and super hard to coordinate. However, if we have clusters, which in practice will likely be smaller or are smaller than entire blockchains, depending on the size of the cluster, corrupting half of them might even become realistic. So for that reason, honest majority isn't good enough for us. Instead, we need to go with what's called dishonest majority assumption. And there the idea is basically that you assume that at least one node is honest instead of assuming that half the nodes are honest. And so that basically gives you much stronger security guarantees, because you don't have to, you just have to check that at least one node is honest. And if that's the case, then you can be sure everything goes correct. And if it doesn't go correct, you can, basically using that, you can find out who's the person who did something wrong, and you can punish them on chain by slashing or anything like this.
All right, thank you. That is indeed a much stronger security. If we push it to the very extreme, how can you make sure that you have this one honest node in your cluster?
Yeah, that's a great question. And that's also one of the key advantages that I really like about dishonest majority as opposed to honest majority, is that you yourself can enforce this. Let me explain how. So let's say you're a developer of this MXE1, which is let's say some DeFi protocol or something that's handling a whole bunch of money, and is using privacy to keep people's balances or something like this encrypted. And you basically say, okay, I want to use Arcium, but I really want to be sure that there isn't some foul play going on here inside of the cluster when I delegate, when the computations happen off chain. Because there's a lot of money at stake or for some other reason. what you can do then is, the first thing that you can do, of course, is you can make your cluster bigger so that it becomes harder to corrupt every single node, which is what's needed. And the other thing you can do that's very easy and very efficient is that you basically say, let's say you're linking to this one, is you say, okay, I'm going to deploy my MXE and I'm going to deploy my own node. And the advantage of this is that since it's your own node belonging to your own MXE, you can always be sure that at least your own node is going to be honest since you're the one that deployed it. And through that, you can basically have 100% trust in the network since you have dishonest majority, which assumes that one node is honest, and that one node is honest.
Okay, well done. I mean, this gives you 100% security that your MXE is safe. Well, this is pretty impressive. Thank you very much for explaining the Arcium network to our audience. We have more documentation, we have different videos and the Arcium documentation, and we'll link it in the comments below. So thank you again for watching, and thank you, Nico, for explaining.
Thank you. Yeah, thanks for watching.